Now let's not mess around because I'm as excited as you are to find out about open source particle accelerators. Clinton Roy, take it away.
Hello everyone. So this is a work talk. This is a talk I've given many times, so this will go completely smoothly. We've already had some IT issues. That's not to do with Linux on my laptop, it's some other part of the system. So that's an outline of the talk. So a little bit of a warning, there are some medical images coming up in the talk. Some, like a lot of the useful stuff that a synchrotron does is medical research, so there is some medical images inbound. They're all false colour. They're not meant to be true to life. They're not meant to be gory, but if you've had some of the medical problems that the synchrotron tries to help with, that can be upsetting for people. I am an open source software engineer. Nearly all of my jobs have been helping researchers of various sorts. I've had one commercial job, and yeah, never again. I do a lot of teaching and a lot of training and a lot of different roles that I've got. I'm silly enough to help organise conferences in Australia. So LinuxConf.au, everythingopen, PyCon.au, and a bunch of other things that I get roped into. I am a software engineer. I am not a physicist, a scientist, a hardware engineer, a researcher, an academic, or an electrician. There are many people with those skill sets at a synchrotron, so I don't have to do any of that. So synchrotron deals with X-rays. X-rays are part of the spectrum of light. This diagram's a lovely diagram that shows you the relative sizes of the different spectra that we've got in light and the different frequencies that they have. And you can see way down the right-hand side where the X-rays are, that's the wavelengths of light that the synchrotron basically deals with. So if we have a look into that spectrum a little bit closer, you can see that humans like to pigeonhole things, so we've split X-rays up into hard X-rays, soft X-rays, ultraviolet light and things like that. Those particular holes, they're not very well defined. You can see that there's a little bit of overlay between soft X-rays and hard X-rays, which is a little bit oxymoronic, but it helps to it helps people to organise things, so that's why we do it. We've got some images at the bottom that show you some of the different techniques that get used. The different frequencies of light, and in our case, the different frequencies of X-rays, impart different levels of energy. So when you hit a particle with an X-ray of a particular energy, either they'll do something or they'll do nothing. And the differences in response that you get give you different techniques to use those X-rays to discover different things about whatever you're firing your X-rays at. And we're going to have a look at a few of those things. So I work down in Melbourne at the Australian Synchrotron, so my talk is going to be all about the Australian Synchrotron. In the large, it's going to be largely the same information for most of the 50-odd public synchrotrons around the world. The Australian Synchrotron is relatively small by international scales and standards, but essentially it does the same things that the other synchrotrons do, just at a smaller scale. We do some things better than other synchrotrons, we do some things worse than other synchrotrons. It is a research tool. It is a fairly large research tool for looking at very small things. You can think about it like a microscope that uses X-rays instead of visible light. I hope no one at work actually hears me say that. They won't let me back in. It is also a very fancy X-ray machine. And again, I hope no one at work hears me describe the synchrotron like that. So we are a particle accelerator. Synchrotron, so the particular generation of synchrotron that I'm talking about is a particle accelerator. We accelerate electrons to 99.99% the speed of light. Electrons do have a little bit of mass, so we can't make them go any faster than that. like all other particles, they'll want to go into a straight line. We want to do stuff with them, so we use electromagnets to turn them, and we keep them in a loop. So we turn the electrons many, many times and keep them in a loop. Because we have accelerated them to very close to the speed of light, they have a lot of momentum. When we apply a force to them, in order to keep momentum being conserved when we turn them, the electrons, when they turn, release an enormous amount of X-ray light where they would have gone instead. We take that byproduct X-rays, which we call white light. That is a full spectrum of X-rays of all different energy frequencies. We take that white X-ray light, we filter it down to like 1 or 2 energies, and then we fire it at a sample. And what we're looking for is either we modify our sample somehow in a very specific way. Because we've filtered down the X-rays to one particular energy level, we know that the sample is only going to act in one particular way. And how it's going to react depends on the sample and the energy level that you're using. So we're either looking for a change in the X-ray that we can measure or a change in the sample that we can measure. So I don't know if this is going to work given where we are. So let's see if this works. Don't think that worked. That's all right. How about I just skip that because I've got no idea. There is a movie that I've recorded about the synchrotron, but because we just copied that over to the USB stick, because it doesn't look like it's going to work. That's okay. So, after we've converted the accelerated electrons into X-rays, we do a lot to those X-rays before we let them hit our sample. So right up the top left, we've got what we call an undulator. So there are different ways of turning the accelerated electrons into X-rays. The simplest is just a single magnet that we call a bending magnet. Then you've got more complicated devices like undulators. And the undulator is actually a series of magnets, north-south, south-north. And what happens is, as the electron is going through, it bounces up and down. And every time the electron gets bounced like that, it generates X-rays. And they design the undulators such that the width of the magnets means that each bounce accumulates the X-rays right at the end of it. So you get a very strong X-rays out of that. We filter a lot of the X-rays out. So when it comes down to the double crystal monochromator, so chromo, colour, mono, single, that is the really important element of all of the beamlines. That's the thing where white light of all different frequencies and energies goes in, and out the other side of it comes just a single or a very narrow band of X-rays of just one energy. Then we've got mirrors that let us focus it. So depending on how big our sample is, we can focus all of those X-rays down onto a very small point. Or if we've got a very large sample, maybe we don't want to focus the X-rays, and maybe we let the X-rays get quite wide. Every time you do something to the X-rays, you get a little bit of scattering. So what tends to happen is every time that we do something to the X-rays, at the end of that we have slits, and those slits are just like a window, and if there's, at the previous stage, if there's any scattering, those windows stop that scattering, those scattered X-rays from hitting the sample. Because in the end, what we really want is a laser-like X-ray light to hit our sample. So we want them, all of the waves or the particles, depending on how you think about it, we want them all to be of the same energy, and we want them to all be parallel or nearly parallel. That makes it such that the maths that we do on seeing the effects that X-ray has on our sample much, much easier. Now, this is another movie. We'll see if this has any... All right, if you could shift that over. All right, and can I... Sorry, folks, this is much easier when it's on my own laptop. So, this is in one of the X-ray beam lines. And how do I pause? So that big circle thing there, that is our monochromator. And essentially, internally, that is pretty much, looks like a periscope. So we've got two mirrors that are parallel. The white light comes in, the first mirror bounces the energy level we're interested in to the second mirror, and the second mirror bounces all of that energy out. All of the X-rays of the frequencies that we're not interested goes through the mirror. And in the back of the mirror, we have a big blob of metal that we run lots of water past to keep it cool. You'll see there are lots and lots of pipes. Most of those pipes are carrying water. If we don't carry lots of water, lots of things melt very, very quickly. So a synchrotron is an X-ray machine, but it's also a big plumbing device. It's also lots of electromagnets. So when the electromagnets and the plumbing meet, they form a steam baby. And oh, how do I hit that again? I don't know how to get it to play again. Feel free to hit again. I don't do GUIs for a reason. Oh, just jump through it maybe. Oh yeah, that's kind of easier. So the big square there, that's a vacuum vessel, and that's got our two mirrors in it. So that's got a curved mirror for focusing in the vertical, and right next to it, it's got another curved mirror on the other side for focusing on the horizontal. That's lots of safety equipment there. So that one at the end there with the corrugated stuff, that's a safety shutter. That is a one-time device. If we detect that there's a person somewhere where they shouldn't be, that thing moves a gate down very quickly, very forcefully. It'll stop the X-rays coming through and save the person, but it is a one-time operation device and very expensive to replace. Then we go into a hutch. So if you imagine a cut shot where we've moved into our other hutch. So this is the area where the users will actually come and set up their experiments. And that table there is where they can put extra imaging work. That's an automatic focus section. That table there is where users can put any of their experimental equipment. So if, for example, they're wanting to understand how spider silk is so strong, they could put a little apparatus there that holds the spider silk, and then they can apply some force to the spider silk, and they can see how it reacts under different strains, for example. That table there is where they would put such equipment. This, on this beamline, this is a big vacuum box. It's like roughly 8 meters long. We have our detector in it. On this beamline, our detector is essentially a camera, but it reacts to X-ray photons rather than optical photons. It is mounted upside down, but it's a camera. It doesn't have a union, so it doesn't get to complain too much. There's roughly $1 million for that detector there. The reason we've got that in that box is that once everything's closed up and it's under a vacuum, we can move that detector way up the front of the box. So if we're doing experiments where we know that the X-rays are going to scatter a lot, we can move the camera right up to the box, close to the sample. But if we're doing experiments where we don't expect lots of deviation, we move the camera way up the back of the box, and that means we can detect a very small deviation over that 8 metres. A very small deviation will turn into a larger deviation, and we can measure it. All right. Now, that almost worked. All right. So that's the biasax beamline. That's the particular beamline that I've been working on. So that's the one that I've got the most knowledge about. X-rays are X-rays of different energy levels let you use different techniques. There are a ton of techniques. I'm not a scientist, so I don't really understand the techniques. Absorption is the one that most of us will understand. If we've ever had a broken bone, I've had my elbow done. We fire X-rays through it. The solid things stop lots of X-rays. The less solid things stop less X-rays. So your bones stop a lot of the X-rays. Your flesh stops a little less of the X-rays. So in the X-ray picture, you are seeing a contrast between your bones and your flesh. That particular X-ray technique is called absorption. Phase contrast is interesting. That is using the wave-like nature of X-rays when you fire the X-rays. So remember, when we condition our X-rays, we want them to behave very coherently. So they're all firing in the same line. They're all the same energy level. So essentially, they're all soldiers marching in formation. We fire them through a sample, and the sample, some parts of the sample will slow the X-rays down and deflect them a little bit. What we do with phase contrast is we let the changes in X-rays accumulate over a long distance, like 10 metres or so. Then we have an X-ray detector there. We measure the really tiny changes that the sample has done to the X-rays. Then we use a lot of maths and work out what the actual size of the sample has done to make the deviation to the X-rays. I've got a photo of that. Diffraction is one of the older techniques. So this is the star-like patterns that you see. Whenever you fire X-rays of the right energy level at a particular type of matter, you get a characteristic scattering pattern. So you can figure out exactly the physical nature of the atoms in the molecule that you're firing at. Spectroscopy is the very pretty stuff where we can work out what elements we're looking at. Fluorescence is interesting, where you fire X-rays at your sample. You will hit particular electrons with just the right energy level. Those electrons will go to a higher energy shell. They'll then relax, and that relaxation, they'll spit out a photon of a different energy level, and will capture that excited sample electron photon using like a regular camera. So that's very similar to how old-time TVs work, where the electron gun will hit a bit of phosphor and leave a little bit of a glow. It's exactly the same sort of technique, except instead of hitting a bit of phosphor, we're actually hitting a sample. Tomography, it's a medical imaging term that we do a lot of. We do a lot of techniques where we're looking inside physical things, looking for the size of particles. So for example, we can look at steel, which has an internal structure, and we can see if the steel has the same internal physical structure all the way through, or if it's got a changing physical structure. So some of the stuff we do is when a large piece of steel has fatigued, we can look at the rest of the steel using different techniques and work out why it's fatigued. So this is a typical absorption shot, and we can see here where all the bones are. We've got a really strong X-ray response, and where all of the fleshy bits are, like our lungs, we haven't captured too many X-rays there. This is the phase contrast example that I was talking about. You can see the X-rays coming in. They're all... oh, that really does look that bad. It's not my laptop. it's my PDF, so it's definitely my PDF doing that. So all the X-rays are coming in, they're essentially all parallel, they're all the same energy levels. So when we hit a sample, the sample will change the X-rays. We can't measure the really tiny subtle changes in the X-rays, so we let the changes propagate over like 10 meters or so, and at 10 meters we put a detector, and those really tiny changes just after the sample, after they've propagated for 10 meters, they're much bigger changes. We can measure them, and then we do maths to reverse the propagation and work out what sample we actually hit. Phase contrast has this really interesting property where it really highlights changes in density really well. So it works really well in medical imaging, where you've got plasma and you've got cells inside that plasma. For reasons that I don't really understand, it really highlights the difference in salinity from inside the cell to the plasma. And it's good enough that we can do machine learning stuff on pictures coming out of phase contrast to quickly count how many red cells, how many white blood cells, and things like that. Yes, this is the science explained to silly software engineers diagram. So diffraction is one of the oldest X-ray techniques we've got. You take your protein or your protein-like substance, you freeze it, you fire X-rays at it, and your specific physical pattern of materials will always produce the same physical star-like diffraction patterns. So you've literally got lookup tables where they've done experiments where, oh, I know that pattern, that's the lead pattern. And if you know your techniques and you know the samples that you're putting in, like you know the chemistry of the samples you're putting in, what the diffraction patterns help you work out is the physical layout of the chemicals that you're putting in. So that's a diffraction pattern that's come from a synchrotron image. The white bar at the top, in this particular technique, this is fairly similar to what we do on the Biosaks beamline that I'm associated with. The setup that we've got there is that our X-ray beam is firing straight towards our detector. We can't let the X-ray source actually hit the detector because it'll burn the detector out. So what we do is we put a little beam stop in the way. So right in the centre there's a little beam stop. It'll only be like 4 or 5 mils of aluminium, and that's where the core of the X-ray beam will hit. And then there's an arm that we can see, which is the white part, which is holding that beam there. What we do on our beamline, we run fluids on our beamline. So we can run chemicals through our beamline. Lots of other beamlines, they require you to freeze your samples, which is obviously not very similar to what you're doing with chemicals or vaccines or drugs. On our beamline, we deal with chemicals. What you want to do is you want to hit an individual molecule of your chemical with an X-ray and get a scatter pattern. What you don't want to do is get clumps of molecules and hit the clumps of molecules with the X-ray pattern, because that'll have a different diffraction X-ray pattern. So what that ends up meaning is that we run our chemical solutions very highly diluted, so like 1%. So what that means is that most of the time, your X-rays are actually going through a buffer solution, like just plain water. And that means that most of the time, most of your X-rays are going straight through. So what we end up doing is we put a diode in that beam stop so we can work out how much of our X-rays are actually hitting that beam stop. And we can work out precisely when we see the beam stop count go down, we know that we've got a molecule of our sample in the way, and that's when we need to look at the diffraction pattern. So we are always looking at different ways of cross-checking our data that's coming in. Tomography. So this is where you take individual slices of a, I can't quite remember This person looks like they've got an entire brain, so that actually looks like a healthy individual, but I imagine that they're not. So one of the things that you can do with a really powerful X-ray is you can go through lots and lots of matter very easily. So in our really powerful X-ray beamlines, we can quite easily go through an individual and map an entire individual if we need to. And you can see here, this, I think that's the brain. Also not a doctor. And you can see at the base, we've got the bed, and then that looks like a pillow, and then we've got the person there. So yes, we're getting really highly detailed scans of our bedding as well as our patient there. So we get a lot of questions about the synchrotron, like why is it so big? When our X-ray beamlines are commonly like 2 or 3 millimeters, and that's our samples are that small, why does the synchrotron itself have to be so big? X-rays scatter in air. So whenever you've had a medical X-ray, one of the things that will happen is that they will put the detector very close to where the shot's being taken, and they'll put the source right next to it. So they want to limit the amount of air that happens. So if you're seeing any fuzziness in your medical X-rays, it's because their equipment is cheap, but it also means that they're not putting you in a vacuum. So it means that some of the X-rays are scattering. In most cases, you don't want to be in a vacuum, but because our samples are very much not alive, we can put our samples in vacuums or very close to vacuums. Vacuums need a lot of equipment to keep them at vacuum level, so we have a lot of space taken up by pumps and things. We use a lot of power to generate our electrons. We use a lot of power to turn our electrons. We use a lot of power to filter out all of those X-rays. All of that generates a lot of heat. Any of the electrons, any of the X-rays that we filter out, they hit metal, and they will heat that metal up. So all of that stuff we've got to keep cool. We do have some of our electromagnets are superconducting electromagnets, so they're in helium baths and they're surrounded by water baths. So some of our processes, if you look at them by volume, they're mostly a plumbing problem rather than a physics problem. Because the accelerator is the largest component, if you make that really large, you can actually fit in more beamlines and you can do more experiments. So there's a scale factor where for your public infrastructure, if you can run 30 experiments at one time, it's cheaper than running a smaller synchrotron that only runs 10 experiments at the same time. Most of our beamlines are within the main circular building. Some of our beamlines are outside of it. So particularly our medical beamlines, what we want to be able to do is let the X-rays widen out so that when you put a person in front of them, we can flash that person's chest, for example, with one X-ray hit. We don't want to have to keep the person in there and move the person around a 0.5 X-ray. Hopefully I'll be able to play the other movie after that and show you some of the colour coding systems. Because we're dealing with X-rays, we have to protect the people around them. So all of these experimental hutches are covered in different materials depending on the strength of the X-rays that they're producing. So this means that most of the walls are like 50 centimetres and more thick of concrete. Sections have got 10, 15, 20 centimetres of lead. That's very heavy, so then you need to have physical structures to hold that up. So the physics side of this is fairly straightforward. The engineering side of it is a world of fun. So it means that to generate a very small X-ray beam that's very finely collimated and filtered can take an entire building to get working right. So we do a lot of medical work, we do diagnostics, we are looking at cancer treatments. We do a lot of looking at particular cells, so there's a lot of biological work. We do some cultural history stuff. I mentioned before about spider silk. There's a whole bunch of work that we can do where you can look at the physical structure of materials. You can apply stresses and strains to them and see how they change. You can also heat them up. You can apply magnetic fields to things. You can apply electricity to things. We've got some things where we're doing things where they are spraying different chemicals at materials and seeing how they change under the X-rays. So a lot of these things we're doing experiments in real time, seeing how a material or a product or a thing changes over time. There's a lot of battery stuff going on, so we will put different, like new fancy, like every other week there's a new battery chemistry that gets put out. 6 months prior to that, it would have been in a synchrotron somewhere in the world, and they will have charged it and discharged it under the synchrotron, trying to work out all of the chemical reactions that are happening that cause that battery to charge, discharge, and try to estimate the total lifetime of that battery. We do a lot of biology, particularly on the biosex, so the bio is biology. So typically for an experiment, we have a researcher who comes up with an idea. They've got a particular material or chemical, and they want to know the physical structure of it. That's a typical problem. You know, it depends. It's different across different areas, but essentially they'll have someone who's used a synchrotron before and will tell them, you need time on an X-ray beamline. So they'll put in an experimental proposal with us. Our scientists will filter through them and look at the ones that they think have the best shot of working. They'll make sure that we've got the right equipment for them. There's normally a lot of communication going backwards and forwards. The synchrotron runs 24/7 when it's running. So if you get an experiment accepted, you'll get given a range of dates, like 3 or 4 days, generally speaking. Depending on the beamline and the experiment, you'll get given some accommodation on site. We're in an industrial area. There's no real nice hotels or anything nearby, so we have a hotel on site. You'll come, you'll stay here. At 3 o'clock in the morning, you'll get a phone call from the operators saying, your beamline is now free, wake up, go and do your experiment. Yeah. It depends on the beamline. So some of our beamlines are very powerful, and it's very likely that the samples that they bring will get destroyed by the X-ray. So typically what will happen is that they'll try to bring not just one pressure sample, they'll try to bring like 10, 15, 20, 100 pressure samples in the hope that with one of them, they'll get lucky and they'll get the data out of the synchrotron that they're looking for. Some of the beamlines, like particularly the soft X-ray beamlines, they won't damage your materials. A lot of the higher end energy ones, like the one I've been working on, we run liquids. So we often, like at the moment, because we're still going through our initial commissioning runs, we will accidentally boil our samples, and we'll see little bits of steam coming off our equipment and sort of reach for the off button. So as a software person, I'm responsible for writing data that makes the hardware work, that makes the experiment run, that aggregates all of the data and then lets them analyze it and lets them download the data later on. Depending on the beamline, samples that you can bring can be essentially anything: gas, solids, liquids, paintings, lots of archaeological stuff, which is always very cool. You do lots of different things to your samples. You can put them under pressure, you can heat them up, you can run gases over them, you can put them in magnetic traps, you can put voltages. Anything that the users can think of that we think is safe, they can do. One of the techniques that we're using on the BioSax beamline is called CoFlow. So the So this is 3 shots of the same equipment here. We have a glass capillary. This glass capillary is like roughly 1 millimetre wide. So the yellow on the outside, the yellow-brown on the outside is the glass. The red in the centre is our sample, and the blue is our buffer. What we do here is that we have the glass, we run our buffer, the buffer touches the glass, we run that fast enough such that in the centre of it a little well forms, and in that well is where we put our sample. And the whole goal of this is to make sure that our sample does not touch the glass. So you can see in the middle that's working appropriately, and you can see on the right where the sample is spread out a bit. Right at the bottom there we've sort of lost our co-flow run. You've got to get the pressures just right. The idea here is that if and when we cook your samples and turn your proteins into curdled eggs, they get trapped in the buffer column and they just get flushed straight out. What we're trying not to happen is getting your samples cooked onto the side of the glass, because that means we've got to stop the experiment, pull that little capillary out, clean it, which is not like that, it's very detailed, and then put it back in. So the whole idea of this sort of system is that we can batch experiments. So a lot of the work that I've been doing and continue to do is batching work. So using techniques like this, that instead of carefully running 10 samples, we can put 100 samples in and we can run them. And if we burn the samples and turn a milk product into curdled milk, it doesn't matter because it's in the middle of a buffer and it'll just get flushed straight away. Getting the pressures right for all of the different sorts of pumping is fun. This is a sample holder from the Sachs wax beamline, the predecessor to the, or the leader to the Bi-Sachs beamline. Each of those holes we can put an individual sample in. So the whole idea here is that in the old days, you had a big vacuum chamber, you open it up, you put your X-ray paper in, you lined your sample up, you looked at it by eye, you said that's good, you closed it all up, bolted it, turned on the pumps, 3 hours later it was pumped down, then you close everything up, you run your experiment, excellent, you open everything up, you vent everything, that takes another half hour, you open up, you go, damn, I misaligned my X-ray paper, start again. What we're doing is trying to make everything as automated as possible so that when we fill that with 100 samples, we put that in, we can line and calibrate the samples remotely as we're going. So we can run 100 samples in like an hour versus running one experiment in a day. So it's all about being able to maximise the uses of the facility without really changing the basics of the facility stay the same, but it's just right in that last gap with sample handling that we're improving things. So the synchrotron's been around for a long time down in Melbourne. I've been there for 5 years now. The funding I got was under a really cleverly named project called Bright to very roughly double the number of beamlines in the facility. The original beamlines were all sort of done as separate projects, which meant that all of the different experts who were working on it, all of the physical people, all the electrical people, the controls people, the software people, they all did things in their own idiosyncratic way, which means that if you're getting an electrical person to try and fix up something on another beamline, that other beamline's done it in a different way and the electrician doesn't want to touch it, or the controls person doesn't want to touch it, or the software person runs screaming away. What we're trying to do with the new beamlines, is try to design all the new beamlines in the same way as much as possible. So, 80, 90% the same. So we have the same physical layouts, we have the same electricity set up, we use the same control systems, the same safety systems as much as possible, such that we can share expertise and knowledge, we can standardise things. When a motor dies over here, we've got a spare here because we're all using the same sort of motors, unlike what it is now. Our users go all the way from first-timers who've never been in a synchrotron before, all the way up to chief scientists who've been using synchrotrons for 20 years. So we've got to write software that sort of caters for that. I mentioned before that we run 24/7, so I target a functionally drunk person, someone who hasn't been sleeping right. They've just travelled all the way from Perth or Singapore or New Zealand or Hong Kong. They might not have slept. So I've got to make our interfaces really simple and easy to use and hard to do bad things. So we make it really hard for them to accidentally delete data. We make it nearly impossible for them to do anything dangerous. Some of our beamlines work really well with remote experiments where they can mail them in. They're really standardized. Some of our beamlines are very bespoke and the users need to do a lot of work. It all depends on the different types of experiments and beamlines. Some of our beamlines, particularly our imaging beamlines, like where we do tomography, we generate a lot of data for each experiment. It's not really feasible for users to download that data or to load it on a hard drive and take it away. So we have a lot of storage on site, and we keep that data on site. We provide analysis software so people can remotely log in and do their analysis work on site, so they don't have to sit there and wait for 3 or 4 days for the data to download. They don't have to bring in a suitcase of hard drives to take the data away if they don't want to. So we're doing a lot of work to simplify a lot of those systems. So the work that when you're doing an experiment on the beamline, you have a certain set of tools, and we're trying to make it such that when you work remotely on your data, like when you go back to your home facility, your home university, and you remotely log in, the same tools that you used on the beamline during your experiment, you've got available to analyse your data. So getting onto the software side of things, that's our stack. So we have, essentially Synchrotron is a robot, but it's tied to the ground, but lots of things can move around so that we can align our beamline. We have a lot of motors, we have a lot of detectors. So we have X-ray detectors of all sorts. We have lots of different sample handlers. So some of our sample handlers are really simple, some of them are really complicated. So we've got some things that are just like ABB arms, where they can pick a sample up and can move it around and rotate it and do all sorts of things. Some of them, it's just like that sample plate that just had 100 holes in it, and all we need to do is drive it left and right, up and down. Full gamut. We use an open source protocol called EPICS. EPICS is used at lots of particle accelerators, so things like CERN. It's also used at nuclear power plants. It's not necessarily the protocol that you would pick today if you were doing a greenfield. It's been in use, so our new beamlines, we're just continuing to build on top of that particular protocol. So EPICS is very much a low-level C++ device driver. It is a network protocol, so it does spit things out on a network. So on the other side of that, we have a Python abstraction called OFID, which can talk to EPICS. So we've escaped C-land, and we can now control our scary robot in Python. On top of OFID, we've got a thing called Blue Sky, so OFID deals with a lot of the low-level details. Blue Sky deals with a lot of the big, high-level details. So Blue Sky is for running experiments, so we can turn on all of our motors, we can turn on all of our pumps, we can open all of our shutters, we can let the X-ray beam through, we can maneuver the samples around in the way of the X-ray, then we can trigger our detectors and take images. Blue Sky does all of that for us. Got a user interface on top of that. I'm not a user interface person. That's a very particular skill set that I don't have. I hate GUIs, I get confused by them. I think icons are the worst invention in the world, so I don't do the GUIs. So EPICS is open source. It is got quite a lot of history to it. There's lots of different versions. Some of those versions are incompatible. We use a fairly small, select set of features that is compatible with a lot of versions. There's a lot of different records. So essentially every device gets described as a record, so you can think of it like a C struct. Some of those fields are readable, So things like a temperature sensor will have a temperature field that you can read. Some of those things like a motor, they'll have two fields that we're really interested in. They'll have a set point field, which you can write to, and that's saying, "Dear Mr. Motor, please move to position 50. It'll have a readback field, which tells us where that motor is. So I'm at 48, 49, 50. So there's a lot of standard records for a lot of standard equipment. We also have you can also make custom fields. So we have a lot of custom fields, a lot of custom records at the synchrotron. PyEpics basically wraps the C library in Python so that we can access it. OFID is the layer that sits on top of that. We can have a lot of high-level abstractions for running an experiment. So we have a trigger event. So we get the machine to do the thing that it's good at. So in the case of a detector, that would be triggering the detector. So it would take an X-ray shot. We have devices that we can read from. So if it's like a temperature sensor or a humidity sensor, we can read from that. But we don't really care what the underlying device is. We just say read, and that device knows how to read itself. We get a lot of data, we get a lot of metadata. So our big overall goal is, at the end of the day, when you go away with a data product that has the data that's collected from your experiment, that's got enough data and metadata about the state of the beamline that in 6 months' time, 12 months' time, if you want to come back and redo that same experiment but tweaked a little bit, there's enough data and metadata in your data product that you'll be able to set up the beamline in exactly the same way that you had, and then just tweak things slightly. So Blue Sky is the high-level orchestration system, and I get to write lots of high-level plans that stage, trigger, read all of the devices on the beamline to run an experiment. So typically, I'll be organising, like to run an experiment, I'll be moving like 150 motors, I'll be firing off maybe 30, 40, 50 detectors. We have a lot of temperature detectors. We only have like one X-ray detector or two X-ray detectors. We might have some other auxiliary devices like spectrometers and stuff. Plans are recipes. We can plug those recipes together. So we can make lots of little Blue Sky plans and then plug them together to make one big Blue Sky plan, which is very helpful because it lets us split the development load. And the really, really important thing is when we tell a motor to move, we get all of the metadata about that motor and we get a full log of how that motor moved across time. So we know how quickly it accelerated. We know, like most of our motors have temperature sensors in them, so we get advance warning if any of the machinery is starting to show signs of wear and tear. So the output of a Blue Sky run is a Blue Sky document. Essentially, all the Blue Sky documents, they have a start document and a stop document, and then they have events. So your typical thing is you start an experiment, you move the motor, so you move the sample into the way, then you trigger your X-ray detector, and then you get a reading from that X-ray detector, so those blue documents. And Blue Sky gives us that. Then we take all of those Blue Sky documents and we put them into our final data product, which is a HDF5 document, which contains all of the data and all of the metadata. Blue Sky makes it easy for us to have an overall plan where we're controlling things. So that top row there is where we're actively doing a plan. That middle row there is where we're monitoring the beam current. So we're making sure that the beam line is still producing X-rays. If we're in the middle of an experiment and somebody does something silly at the other end of the synchrotron and we lose X-rays, we want to know about it because we want to pause the experiment because there's no X-rays. So asynchronously, we're monitoring a bunch of things and we don't have to think about doing that. We just tell Blue Sky, while we're running this experiment, please monitor this epics record, and if it changes from good to bad, just pause the experiment. And down the bottom there, we're monitoring temperatures. On the biasax beamline, we've got like 40, 50 temperature sensors. If anything happens to the focus of the X-rays and the X-rays veer off where they're supposed to be going, they'll hit a bit of metal. That metal will heat up and one of these temperature sensors will go up. And very quickly we'll get an alarm and we'll figure out that something's wrong and we can close the shutter and stop the experiment. So that's very much a safety thing, but it also means that if we get a temperature spike somewhere, that means that the X-rays are not hitting our sample, they're hitting one of our shields, and there's no point keeping going with the experiment. I do CLIs, I don't do GUIs. I am really excited about the future of GUIs, particularly web stuff. We really want to do stuff through the web because we want to make it such that if you're doing an experiment at the synchrotron, later on at home, you can use the same toolkit to do your analysis. I don't want to have to write, I don't want to have to support software that gets installed on people's laptops. That's kind of the end of it, really. So that's sort of the content of the talk. I do have some interesting stuff that the synchrotron gets used for. I don't have any control over the shaking of that, I'm sorry. So if you are unlucky enough to get cancer on an organ, one of the, and again, not a doctor, not an oncologist at all, one of the approaches that you can take for solving that cancer is firing an X-ray beam at it. Typically, that'll be like 3, 4, 5 mils square of X-rays fired at the cancer. And they'll fire it into the person and then they'll rotate the person to minimise the amount of non-cancerous flesh that gets hit by the X-ray beams. Some very clever people, some very scary people, realised that if you fired X-rays in the form of a comb, so you can see the lines going through and you can see the comb-like form of that. So instead of firing a solid block of X-rays at the cancer, if you fire a comb, and each of these combs is very, very thin, you can actually destroy the cancer without harming any of the non-cancerous cells in the way. Don't ask me how they discovered this. I'm not sure, at least at the time when I was putting these slides together, I'm not sure they understood the mechanism. So, you know, it's a little bit like headache tablets and things like that. We know they work, but not quite sure entirely how they work. So because they discovered that physically masking the X-rays and firing them in these really thin comb-like structures does not hurt the non-cancerous cells, they amped up the X-rays. And they discovered that they could, theoretically, cure cancer with one shot of X-rays, much higher than what the textbooks would say if you're using a full beam of radiation. We've done, I believe, 1 experiment on a dog at the Australian Synchrotron that had a cancerous lesion on his paw, I think. And as far as I'm aware, that went well. So long term, if it continues going well, this could actually be a really good answer to treating cancer that's internal. So say you've got a cancerous lesion on the brain somewhere where you can't slice and dice into it, and the promise is that it would be a one and done operation because you can hit it with so much X-rays that it doesn't harm the non-cancerous tissue. So not a doctor, not an oncologist, I don't know anything about this particular thing, but we're starting to experiment with this at the Australian Synchrotron, and I think the Japanese synchrotron as well. So like, I don't understand how any of it works, but it's extremely interesting and very cool. A certain percentage of the population that gets mammograms, the particular energies of X-rays that gets used at a lab source does not produce mammograms that have a lot of contrast in them. I think the terminology used there is that that particular individual has dense tissue. One of the things that we're also looking at the Australian Synchrotron is being able to use synchrotron X-rays, which are much more finely calibrated than a lab source that you would typically get to do mammography. So here we can see a mammography result using synchrotron X-ray radiation. And this person, when they had a traditional mammography, came back as basically all white, dense tissue. And you could not differentiate between the healthy cells and the potentially cancerous cells. So this is something that the Australian Synchrotron's looking at the moment. It's not going to be a simple thing to do. If you are going for a regular mammography, it doesn't matter how tall you are, because you can walk up to the machine and they can move the X-ray machine down to the appropriate height. With the synchrotron, we can't do that. So what we have is a bed with a anatomically correct structure for the person to lay down into, such that their breasts are aligned appropriately. We have that bed on a big ABB arm and we move the entire patient around. So long term, I think the idea is that if an individual, they've gone and they've had a regular mammography result come back and it was inconclusive, they'd then line up at the synchrotron to get this sort of technology used on them so that they can get a high contrast, useful medical result. So that's something that's also being worked at the Australian Synchrotron at the moment. Synchrotrons were used to be able to take images of malaria. Malaria has a hilariously complicated life cycle. It goes in and out of multiple warm bodies across its life cycle, and it's very difficult to track. And synchrotron techniques are pretty much the only technique we can use to begin to uncover them. And in really exciting news, the synchrotron techniques that are used to understand the physical structure of things like malaria, this year we've got vaccines that are being rolled out in Africa. If you can imagine the sort of economic improvement that could be had if 20% of your GDP wasn't taken out every year, again and again, you can sort of see the positive outcomes that something like this could have for the world. We do a lot of cultural work. This is a very popular one at the synchrotron when you do tours. So it's very common if an artist has done work and they're not particularly happy with it, that they'll reuse that canvas again and do another artwork on top. So if you have a look at the top of the, I'm not sure if that's a hairstyle or a cap on top, but if you notice that particular wavy line at the top, and then you flip that image, you'll see that wavy line down the bottom. And then if you have a closer look, you'll see that there's another face in there. So this particular painting was reasonably famous, and then work done at the Australian Synchrotron has shown that there's a second painting underneath it. And I think there's a little bit of a story, like I think maybe that was the wife and that was the mistress, I think. The things that the synchrotron is really good at doing is showing you the physical structure of proteins. So PCD is no, I can't remember it. It's a particular disease that affects all sorts of birds in a particular family. And this is the physical layout of the, I think it's a bacterium that we can use to then go and create a vaccine for it. So we've got a vaccine for it, so hopefully that will help that particular bird population. So a lot of the time you can work out the chemistry of something, but you need to know the physical layout of it. So the typical analogy for vaccines is that the germ has a particular physical shape, so that's the lock, and the vaccine has to take that particular physical shape to fit into that. And that's where a synchrotron can be very useful. This is one of the prettier beamlines. They produce a lot of false colour photos, and they're very good at showing you what elements are in particular samples. So here we've got some wheat germ cells, I think they are, and they're highlighting with the false colours the particular elements in them. So you can use this, like if you want to breed a particular type of wheat that's got a lot of iron in it, you can breed up 100 generations and then take them to the synchrotron and work out which particular germ lines have the high iron, and then go crossbreed those and go for another generation. And I think that is my last photo. So I don't know if I've got time for questions. I'm good for questions if you've got time. With the caveat that I'm not a scientist, I'm not a physicist, and I'm just a software person trying to get along.
We're 5 to 5. Yep, we've got questions. Go up the top and work my way down. Oh, got a lot of questions. Who was up here that I saw first?
When you were mentioning there was that safety shutter, why is that such an expensive thing? Isn't it just like slam down closed?
Yeah, it's got to be very quick, but it's also got to be very sure of itself that when it closes, it will block the window aperture into the next shutter. If that thing fires, it generally means that we think we've discovered there's a hutch while there are X-rays. So it's like the worst of all possible situations is happening, and we need to stop this now.
Hey, can you talk a little bit about the open source projects? Do you talk to the upstream people much and contribute and kind of?
So Epix is very much a hardware type project. So it's still getting new versions released, but we don't really touch too much of Epix because we've already got a rollout of Epix at the moment. We can't really upgrade our version of Epix too much. Blue Sky, we have a really good working relationship with some of the American synchrotrons, and we commit a lot of changes upstream to them. And all of the other scientific bits of software that we use, we're always applying patches upstream to that as well. Yeah.
G'day. Just wondering. I can see the sort of whole software line in the beam line, but is there software that has to run the actual accelerator and beam generator and everything?
So a lot of that stuff is Epix, essentially. There's a lot of stuff which is hardware controlled. So things like when the electrons are going around in the ring, you've got to have a very fast response feedback on that. So anything that's got that sort of timeliness on it, there'll be hardware approaches to doing that. Epix, very roughly, works at about 10 hertz. So if you're doing something that works in about the 10 hertz range, we'll use Epix for that. Otherwise, we'll use different solutions.
I'm going to sneak in a quick question. The breast image that you had where it showed the different colours of different densities,
Yep.
was that particularly pointing out damaged tissue?
I don't believe so. Not from memory, I don't believe so. I think that was very much I think that was part of the control group where they'd had a mammography and it was clear, and then they were using the synchrotron radiation to get at least a baseline of what good breast tissue looks like with the synchrotron radiation. Please go ahead. I'm just trying to find a video.
With the software libraries, you talked about the Epics and Blue Sky libraries. Are they used exclusively with synchrotrons, or are there non-synchrotron applications? And could there be such applications if there aren't already?
Yeah, so OFID in particular is an abstraction that sits on top of a hardware abstraction. So there are two hardware abstractions that it sits on top of, Epics and Tango. Tango does get used, so Epics is like the old one and Tango is like the new one. It's very possible, and some people are using OFID, and if you use OFID with it, you can use Blue Sky with it. There are definitely science labs who have got like science X-ray sources who are using Blue Sky, so they're not a synchrotron, but they're using a lot of the same equipment as the synchrotron. You can use it for anything that you can make an OFID device for. You can use Blue Sky on top of that. It tends to be science equipment, and Epics tends to be the sort of thing that only people who work at synchrotrons and nuclear reactors know about. So it doesn't advertise itself very well outside of that.
The obvious question being, given that safety critical hardware is involved here.
Yep.
How well tested is all this?
So we have in the software world. In the software world where we are, we basically say we don't do safety critical stuff ourselves. We have two safety systems involved. We have a personnel safety system, which is designed exclusively to protect the humans. Then we have an equipment safety system that is designed to keep the equipment safe. These are hardware-based, so they're PLC hardware-based, and these are totally separate systems to all the control systems. So we rely on those separate hardware systems to keep people safe and to keep the equipment safe.
Just wondering, is there a public open day coming up?
I don't know. So before COVID, we ran open days every 2 years. I think we must be gearing up for one soon. They're quite interesting days. So we've got to time it such that the accelerator itself is off. So we have deep maintenance periods every 3 or 4 months where we turn everything off and everything goes cold, and because that's the only time that you can really go in and mop up and clean up and do lots of maintenance work. And every couple of years during one of those maintenance periods, we decide to hold an open day and we let the public come in and have a look at all the equipment, because the vast bulk of it is paid for with public funds. I don't know of when the next public day is coming up, but I can certainly make sure that when it happens, I'll put it on like the Linux Australia mailing list, for example.
I'm quite interested in the... you said you're putting new experiments onto the synchrotron.
Yep.
And you're trying to consolidate hardware, etc. Does that mean there's extra slots that you're able to tap into? And are you able to go back to some of the older experiments and retrofit them with the newer hardware?
So we are a very oversubscribed instrument. I think, like, I'm because I'm not a scientist, I'm not in the panels which is selecting which experiments we can do. So essentially, like 90% of the experiments get picked on merit, probably 99%. We do have a commercial access stream where people can pay, so companies who have made a product and they're interested in it, they can pay to get access to beam time. But like 99% of our experiments are chosen on merit for their scientific merit. We're very much oversubscribed. We can't say yes to every experiment we want to, and very much opening up the new beam lines is about being able to accept more experiments and making it such that we're not running one experiment in a night, we're running 100 experiments a night is very much about being able to run more experiments in one session. So definitely the newer techniques that are being made available, we definitely expect some people who've run experiments will want to come back and use newer instruments and newer ways of doing things.
Very small question and then a follow-up. Do you guys still have a moon meter? Because that was a hell of a graph that I remember you guys having at one point. And when it comes to the testing, I more meant in the sense that the control loop, obviously if you guys are trying to get repeatability and batch and automation, you don't want the software glitching halfway through a batch and blocking overnight work. Like, are you testing that extensively?
It sort of depends. So on the software side, I can say that we test our software fairly thoroughly. But so one of the nice things is that Epics is network traffic. So it's very easy for us to write a simple server that pretends to be like an area detector. It accepts the network message to trigger, and it sends out a packet saying, here's the X-ray data. So we can write mock-up hardware servers and we can test the software really thoroughly. The problem comes when the hardware always has more quirks than we could ever think possible. So unfortunately, there's nothing like running actual experiments to find bugs. So the synchrotron runs 24/7. During the experiment time, a scientist is on call. They will help set up the experiment. They'll have a training information pack for the users. That will impart as much knowledge. They'll hand it over, they'll go home, they'll have their phone with them, and hopefully the experiment will run without problems. Certainly what we're discovering on BioSax is that the hardware that we've purchased has a lot of firmware bugs that, guess who's got to fix those? And we're constantly running into weird, wacky things where, this bit of really expensive kit that's meant to do one thing doesn't do that one thing that you really wanted it to do. So the hardware always throws up more surprises than the software. So this video is a walk around of the synchrotron. And one of the things I wanted to point out is you can see the white floor and the red floor. So that's actually two separate foundations. So the white floor is the foundation where the accelerator and most of the beamlines sit on. The red floor is a separate foundation which the building sits on. So if wind buffets the side of the building or, a car crashes into the side of the building, it won't affect the accelerator. You can see the different colours. So you've got the white there, which doesn't really have any radiation protection. You've got the blue turquoise, which is generally we use for lead. And then we have another colour for concrete. So it's really clear what levels of protection you're getting. And that there is our coffee bean line. That's where we have our Friday donuts and coffees. So I should show you one of the interesting beam lines. So way back at the start, wow, this thing is really chugging away. Way back at the start, where I showed you the different spectra that are available, I did mention that there's such a thing as soft X-ray beamlines. You don't actually need a lot of protection from those. You only need leaded glass to protect you from them. So when it comes around to it, you'll actually see a lot of the experimental stuff sitting out in the open. Because the level of X-rays that it produces, they can be stopped with leaded glass.
Okay. Do we have any more questions? Clinton's going to be around. Quite happy to talk about things.
Absolutely.
So thank you, Clinton. It's been awesome. That was really exciting.